The exam is scheduled for this Thursday, Wednesday, whatever. What day is it? Wednesday, Thursday. What day are we?
Right now we're Tuesday.
So it's Thursday. Sorry. I can barely count to 10 or deal with my ABCs. Days of the week are even harder. It's Thursday. Okay, the second day of the week that we meet. There are 38 total questions. Of those, it went a little bit higher than I thought. I'd say 10 to 12 of those reasonably require a calculator. That doesn't mean extensive conversions, but you would probably pull out your calculator and calculate it. For instance, that subtraction. Okay, 1.45 times 10 to the 12th minus 3.2 times 10 to the 10th. You can do that without a calculator, but you would probably do it with a calculator. I counted that as a calculator question, okay, to give you an idea. There are 4 show your work questions. The show your work, more so than the multiple choice, will usually involve multiple conversions. Because if it's just a single simple conversion, you could probably do that in your head and get the answer, and you're going to get frustrated at me for having to show work. So the show your work ones tend to be a little bit more involved, 2, maybe 3 conversion steps within them. Okay? With those are separate from the multiple choice, even though there are multiple choice options. Okay? Some people like the comfort of having multiple choice options to look at, so when they run through the calculation and say, oh, it doesn't match. Okay? It doesn't match one of those options. So those do have multiple choice selections. They do not get entered in the Scantron. Okay? As a pseudo aid for that, the show your work are labeled A through D. The multiple choice are labeled 1 through, any guesses? 1 through 34, because 4 of them are show your work. Okay? And then there's also 1 extra credit question. For the ease of grading, I've put the show your work stuff right at the very beginning of the exam so that when you turn that in, I can very quickly go through, turn the page, grade the show your work, total that, and not have to flip through and find it somewhere in the exam or at the end of the exam. Okay? Most people are less confident with the show your work. Okay? Believe it or not, probably 90% of you, even though you are less confident with that material, are going to start with the very first question, which is show your work. Okay? That is a horrible idea. I cannot stress that enough. Okay? The only time you should start an exam with question number 1 is when you don't have the rest of the exam to start. Okay? That is the only time. Okay? So if you have to go into graduate school, they've got GREs and stuff like that. Those usually are computer generated and they feed you 1 question at a time. Okay? You have the entire exam to look at. Go through the entire exam first. Right? In general, my kind of rule of thumb is if as you're scanning through the exam, you read a question and literally the answer jumps out of the page and starts slapping you in the face, saying this is the answer, then you can bubble in that answer. Until that point, you keep reading the exam. Okay? The idea being that way you can find out what you're getting involved with for the entire exam, and you can be a little bit more prepared when you have to go back through and start answering all the questions. Okay? So please go through and do that. Read your directions and read the exam. Both of those things will help you get calmed and settled for the exam and actually allow you to do better overall. Okay? The more panicked you are about rushing through the exam, usually the worse your score. Okay? Everybody here kind of understand that? Okay. Please. Okay, I might start stomping in the back of the room, okay, when I pass out the exam and see everybody start with page 1. Okay? I'll do it quietly. Okay, but please read through the whole exam, get a feel for what you're about to approach first. Any questions in general about the format of the exam? Scantrons, now I'm down to like 600 of them. So you don't need to supply them. I will supply the Scantrons. All right? That way we don't have to deal with different Scantrons and not reading machines. It becomes a pain. Okay. So what we will then go ahead and do is continue with the rest of the material that we've got planned, which is I think 5 to 6 slides on the last section of material we have yet to cover. Almost. It's going to be temperature and heat. All right, before we do that, we raced through this question, I believe, on Thursday. Should I go back through and reevaluate it stepwise? Sure, I like the optimism there. So, we go through, look at the question. An automobile battery contains 1,275 milliliters of acid. If the density of the battery acid is 1.84 grams per milliliter, how many grams of acid are in the automobile battery? All right. Had a lot of people talk to me about, well, I don't know how to do any of these problems. I don't know the conversions. That's fine. Right? There's only a few conversions that you need to know. Those few that you need to know are your metric system, milli, kilo, and centi. What about all the other conversions that are out there? Because there's a lot of them. I've given them to you. Okay? So don't stress about memorizing those. Focus more on the format on how we set up the question. So with this question, where do we start? As with all conversion questions. What are you trying to get to? So start on the far right, put an equal sign, and what units do we want for our answer? Grams. Right? We now have a couple options on where we would move to next, because we're given 2 numbers to start with. Okay? Which number do you want to look at first, the 1275 or the 1.84? Okay? Should be kind of an even mix between it. 1275, why do you want to start with 1275? First number shown, that's a reasonable guess. I am obnoxious, and I will throw other numbers in there, and they will be the first number shown. So that's not going to work out for the best option. We need a better reason behind it. So we could look at the milliliters potentially canceling with each other. Okay? So what you're used to is setting up the format where you're starting with a number in the numerator and then you're multiplying by conversion factors. Well, the 1.84 is a grams per milliliter. That is a conversion factor. Right? So based on the standard format we've been working with, it doesn't make sense to start with the conversion factor because we haven't been doing that. Okay? That doesn't guarantee that's the correct option. Okay, so let's look at why we might start with the 184 or the 1 point. It has the target unit that we want in it. That 1.84 actually has grams as part of its unit value. And we want grams as our answer. I would argue that is a better place to start because I know I'm at least getting to the correct position, okay, the correct unit. Both methods work. It's whichever one you feel is more comfortable. If you have a limited value of numbers, there's only 2 things here. More than likely, you're going to have to use them both. You could probably start with either one and just get lucky. But if I gave you 6 different numbers in here, now the order that you put them in could really matter. So we want to be very careful with how we approach it. Let's go ahead and start with using that gram value. Okay? Our conversion is 1.84 grams in milliliters. So that does introduce that gram unit. Where do I want the gram unit to show up in my answer? Numerator, denominator? Numerator. Which means if I'm going to put that 1.84 in, I want to make sure that when I use it, the grams show up in my numerator. If they showed up in the denominator, that doesn't work to get to my answer. So far, so good? What number shows up in front of milliliters? 1. Why not 1275? I'm using the conversion factor here. The conversion factor is right here. Those are the numbers that I need to introduce. Yes, 1275 shows up in front of milliliters, but it's just milliliters. In this unit, we've got grams and milliliters. We can't bring the 1275 in yet. What number shows up in front of grams? How do you know 1.84 shows up in front of grams? You almost always see your conversion factors written out like this, right, with that nice little slash. We very rarely ever see them written out as they truly mean. 1.84 grams equals 1 milliliter. Right? Or, written out even better, 1.84 grams in 1 milliliter. Bless you. Why do we write it out in that first case? Why is it always written out like this?
Formatting.
What's that?
It's easier formatting.
It's purely formatting. No other reason than formatting. It doesn't make sense to use the nice equation numerator-denominator format because that's too difficult to type. Okay? It doesn't make sense to use the equation format because that involves more lines. We're lazy. Okay? And you don't pretend to me like you're not lazy. I know you're just as lazy as scientists are. Okay? So once we've got our conversion factor in here, we do have the grams in the numerator, but we also have milliliters in the denominator. Does that show up in our answer? No. So that means the next thing I drop in here has to cancel that unit. Okay? And again, I want you to get used to this pattern. We're now going to multiply by something. That something needs to have milliliters in the numerator. Okay? What number did I put in front of the milliliters? Careful. What number did I already put in front of the milliliters in my numerator? I have specified absolutely no number. Why? I'm trying to track my units. I don't care what the mathematics is yet. I don't care what numbers go in there yet because I'm not about to punch it into the calculator. What I need to find is make sure my units are appropriate and work. If my units work, then I can deal with the numbers and I can get a correct answer. If I track my units, what happens after this multiplication? The milliliters cancel and I would have what units? Grams. That is the unit that I want. So now that I know my unit is correct, now I can go back through and drop the number in front of that milliliters. What number shows up in front of it? 1275. What number shows up underneath? 1. Okay. Why 1? All of our calculations are numerator-denominator, the top and bottom based. Okay? So what we want to deal with is make sure that when we put something into the denominator in this case, that it doesn't change our other number, our other value. If it changes it, then we've got a problem. Okay? Since the number we're dropping in is just 1275 milliliters, I don't want to put in a unit in the denominator, and I don't want to put in a numerical value that will change 1275. Yes?
I got an answer. Just one battery.
Huh?
Just one battery. One unit, which you're trying to figure out the weight of.
Yes, we would assume in one battery. Yep. Because, yeah, it starts with a single battery holds 1275, and it says in an automobile battery. It's a fun question. Should we level this one up a little bit? Yes, no. Okay, I'm hearing yeses and no's. So let's deal with heat and temperature, and we'll come back to doing this one again with it a little bit more difficult a little bit later. Okay? Any other questions with it? Okay. Temperature. Temperature is a measure of the average kinetic energy of your particles within an individual sample. Okay? Just kind of an odd thing to say. It's very nebulous. When we think about temperature and heat, they are relatively confusing terms. Temperature is just a way that we can measure that average kinetic energy, get some idea of what the energy is within that system. Okay? Because, of course, this is something that has existed from the beginning of our time, we end up having to come up with different people discovering it and different people monitoring it. which means, of course, we get different unit systems. Okay? So we need to be able to convert between those unit systems. Fahrenheit is the one we're used to. Okay, we should really call it American, but because the English don't use Fahrenheit. But we've got the American temperature system of our Fahrenheit. Then we have Celsius, which is used pretty much universally throughout the world for general temperatures. And then when we move into science, we come to another system that's Kelvins. Okay? So why have 3 different systems? First off, Fahrenheit and Celsius. Okay, we can kind of compete between those two. Why don't we all just use the science system? Or why don't we just use the Celsius system? Well, a lot of that comes back to physics and thermodynamics and all sorts of other fun things that we would have to deal with. Okay? All of these are based off of certain evaluations. So your Fahrenheit and Celsius are ultimately coming back to water and looking at where the phase changes occur for water. Okay? And then they decided to drop those temperatures in those ranges. So we could go through and look at all of those values in our Celsius. And if you really, really wanted to, you could go through and derive a relationship between those. Okay? It is possible. I think I've done it once. Can't say I was happy about doing it once. So if you really want to see that derivation, you can talk to me after class and you can go through and deal with it. So what do we expect you guys to be able to do? You need to be able to do the conversion, but to do that, you have to know the equation to be able to do that conversion. Okay? So we'll give it to you, which we'll look at in just a second. Okay? With Fahrenheit, your common water temperatures, it freezes at 32 degrees Fahrenheit, boils at 212. Okay? Celsius, 0 degrees and 100 degrees. Kind of fascinating, because if we ask the boiling point of water, pretty much everybody in here is going to say what? Really? Some people are actually saying 212. Most people say it's 100 degrees, which is very fascinating considering that we're American and we use the Fahrenheit system, yet when we talk about boiling water, we think about 100 degrees. Okay? Celsius. Kind of an odd conundrum, if you will. In Kelvin, your water freezes at 273 Kelvin. There's a slight adjustment to make here. There's no degree. And it boils at 373 Kelvin. So it seems a bit odd. Okay? The biggest issue that comes out of this and why science has developed Kelvin as a unit system is what happens when we get colder than ice. Okay? Is it possible to get colder than ice, 0 degrees Celsius? Yeah, we can get negative temperatures. Those negative temperatures bring in now a negative sign. If you're going to run a calculation, you now have a negative sign that's flipping and changing all over the place. Okay? That makes mathematics a lot more difficult. Okay? Same deal goes for your Fahrenheit. We can drop that temperature to negative degrees Fahrenheit. So we have this sign issue that pops up. Chemists and physicists, as much as we rely on mathematicians, don't like dealing with signs. We develop systems that avoid the sign system. So Kelvin is an absolute scale, meaning it never goes negative, in quotes. Okay. We can reach the lowest temperature, and we can actually get there, of 0 degrees or 0 Kelvin. It's an absolute scale. We're always 0 to some positive temperature. It never drops below 0. That means when we deal with kelvins in our mathematics or in our equations, we never have to deal with that sign changing on us. It makes our calculations a little bit easier to work with. Okay? So how do we go through and convert these? Just checking to make sure I did those equations right. I believe I did. I will provide you with the the Celsius to Fahrenheit conversion. That's that top one. So the way this equation would work is if I want to convert my degrees Celsius, say the boiling point of water, which was what in degrees Celsius? Boiling point of water in degrees Celsius was 100 degrees Celsius for water. We multiply by 9, divide by 5, add 32, and with the calculator, we would get sure hope 212. All right? So that allows us to convert from our degrees Celsius to our Fahrenheit. Did you just verify that?
Yeah.
Good. All right, so if you're given the degrees Celsius, you just plug it into this formula, and it'll spit out an answer of degrees Fahrenheit for you. Awesome. Good deal. What if you're given degrees Fahrenheit and you want degrees Celsius? How do you do that conversion? Well, we could just go back to our equation, use some algebra, and solve it the reverse direction. All right? Which is what I expect you to do. So for practice, that's what you should do. So let's give that a shot. Let's do the derivation of that. Let's say we start with Fahrenheit 32 degrees. How do we convert that to degrees Celsius? So if we do the algebra, we would then subtract 32 from both sides of our equation, which gets us our degrees Celsius times 9 over 5 equals 0. 0 times 5, 0 divided by 9, 0, what's our degrees Celsius? 0. So given that first equation, we don't need the second one because we can do the algebra to shift back and forth. Okay? If you're weak with the algebra, unfortunately what I'm going to tell you to do is you need to memorize the derive equation. Okay? Or practice it a whole bunch. But the only one I'm going to give you is the degrees Celsius to Fahrenheit. Questions? Yes?
They've never reached 0 Kelvin.
0 Kelvin has not been reached. Negative Kelvin has. Yeah. Yes. No notes for the test. Yep. So if you take a look at the first page, I did post the first page of the exam. Okay. The bottom of that, you'll notice there's a list of conversion factors and your degrees Celsius to Fahrenheit equation. So I don't expect you to have that memorized. I will provide that. Last one, degrees Celsius to Kelvin. All right, so to get into the universal system, I am going to ask that you memorize this one. You add 273. That's it. All right, officially, it's 273.15. All right, why do I tell you just to add 273?
Absolutely.
No, because it's still officially 0.15. What's that?
1.5 is never going to go higher.
Kinda. It definitely rounds down to 273, but why would I round down? You will likely only use 3 significant digits, so it doesn't make sense to include the extra fourth and fifth significant digit. Okay?
So to convert Fahrenheit to Kelvin, we would have to convert Fahrenheit to Celsius then.
Exactly right. So if I give you a Fahrenheit number and ask for the Kelvin, you have to convert Fahrenheit to Celsius, and then Celsius to Kelvin.
On the written part of the test, sorry, this is off the subject. Do you expect a one-sentence explanation of the answer?
No, I don't. Your explanation in the show your work for answers is your work. It's all the unit work. So that's what I will track is your units. Because you could randomly punch into the calculator and get the numbers to come out where it matches an answer. And it could very well be the correct answer. But you still had no clue what you were doing. So what I want to see is the unit work all the way through. All right, if you got questions about that, look back to every single conversion we've done. I've been showing you that unit work. All right? Other questions? All right. So, body temperature, 98.6 degrees Fahrenheit. What is body temperature in degrees Celsius and in Kelvin? Any nurses in the room? I guess it could be doctors too. What is body temperature in degrees Celsius?
tell you off the top of my head.
Oh, okay. I was just curious. So, in-class problem. There we go. But that may not help you for the exam. So what we should go through and do is start with the blue box, because that's the one you're given. What we can now do is subtract 32 from both sides. We get degrees Celsius times 9 over 5 equals 66.6. Really?
Oh, yeah, you can't do that.
60 degrees Fahrenheit. What can we do now? Multiply both sides by 5. All right, I'm going to condense this. Divide both sides by 9. And we end up with our degrees Celsius equal to, it's 37 spot on, isn't it?
It is.
Yeah. What answer do we provide? Which might be your question. Give me just a second. 37 degrees Celsius, is that our answer? No. What's wrong with that answer? Sig figs. We need that extra 0. Yes?
Do you mind if we use 1.8 instead of 9 over 5?
What's the difference between 1.8 and 9 over 5? They're the same. Yeah. So, yeah, some people have gone through and sort of condensed it and just done some weird formula for it. I've never bothered to memorize it and have to look it up every single time. Or I approximate. The beauty of organic chemistry. So we now have our degrees Celsius. How do we get Kelvin? Kelvin equals our degrees Celsius plus 273. Depending on how accurate you wanted to get, 1.5 equals 310.15 degrees Celsius. The answer that you would more than likely see would just be your 310. Is there a problem with writing 310? Is that answer technically correct? We do need to, oh yeah, might be nice if I use the proper unit. What kind of operation did we just do here? Addition. When we do addition, what transfers are our sig figs? The least accurate place, our least accurate place, geez, was to the tenths place. So if we use 273.15, our answer needs to carry out to the tenths place, which would then become 310.2. Which is exceedingly frustrating, and I completely agree with you. This is why I think how much we complain about sig figs is a load of crap, because we're not consistent with it. Okay? So watch out with your sig figs. It's a multiple choice exam, so more than likely, unless I'm directly testing you on sig figs, you won't have to worry about it, because all of your answers will have the same number of sig figs. Yes?
So, a question like this on the test, would it matter which?
I would not put 310.15, 310.2, 310.1, 310. I would not provide those answers.
So, do you mind red box or blue box?
I don't care which equation you use. So if you bother to memorize the red box, by all means, go ahead and do it. Okay? If it's a show your work question, it's actually a horrible question for show your work. Okay? Because it's just a question of multiplying out. There really is no unit conversion as we've seen it. Okay? So it doesn't make sense as a show your work question. Okay? I would still give you credit for it. And yeah, I'd look at it and be like, this was a dumb question to ask for show your work.
And the only time on Kelvin we use 0.15 is whether or not there's enough sig figs.
If we want to use those sig figs, it's really a choice.
But you won't dock us.
I won't dock you on an exam. By definition, we tell you to use 273. The 0.15 is just because sometimes random numbers stick in my head, and that happened to be 2 of them. Okay? Questions with your temperature scales? Kind of straightforward, right? Heat concept. So temperature measures the average energy. Okay? Heat is an expression of the total energy. So if we were to look at the energy within an individual system, each particle contributes some amount of energy. Right? Temperature is going to measure the average energy for that whole system. So if we took the energy for the classroom right now, we would have a spread. Some of you, though very few of you, are extremely high energy and excited to be here. Maybe it's not that case. A lot of you, or no, let's hope that's the some of you again, okay, are so bored you're falling asleep in the class. Okay? In theory, everybody else is somewhere in the middle. So we could take an average reading of the temperature, and I would say I'm doing okay, because not all of you are sleeping and not all of you are super excited to be here. Okay? So we've got somewhere in the middle. We're looking at an average class moving forward, kind of understanding the material. But if I want to look at the total energy, I'm going to look at how every single person contributes to that overall system. Okay? That I'm going to look at a different unit system for. Okay? That's your heat. Okay? The measure of all the energy in an entire system. That energy gets expressed in its own unit system, either joules or calories. Calories is typically your English system. Joules is more your, I keep calling it sci-fi. SI, the SI system, okay, your metric standard science system. Okay. As an interesting way to observe that, we could look at these two containers. Both of them record the exact same temperature. But if we dumped one of these, if one of these was forced to be dumped on you, which one would you prefer to have dumped on you? The smaller one, because there's less heat is going to get transferred into you. You're concerned about the total energy of the system, not just the temperature. Okay? So it's kind of and it is kind of morbid because I always go back to that inflicting pain. But we tend to have a pretty good threshold for deciding what's painful and what's not, so it works well. Okay? So your heat is looking at the total energy, temperature is just looking at the average. How this can end up getting related through for actual mathematics. So a lot of this course, you will see a lot of mathematics pop up, and then we kind of show it to you, and then we take it away and say, don't worry about it. This is one of those cases. Okay? What we can do is look at the specific heat. So every species or every compound is going to have a different way to relate that energy or how it transfers that energy. So we can look at the joules per gram degrees Celsius. So what are we saying by this? This is really saying that we've got an energy involved in changing a mass by a temperature. Okay. So if we look at an individual species, like our water in that previous case, okay, it's going to require more energy to heat up that 100 mil volume than the 500 mil, or the numbers, 1,000 mil volume and our 500 mil volume. And that's because there's a larger mass. So I'm going to need more energy to get all of that mass heated up. Okay? So we're trying to relate something about the mass of a species, the temperature that it's going to change, and the energy required to put into it. Every species has a slightly different specific heat. Okay, well, is that actually true? Okay, what do we cook with? What kind of pots and pans do we use? What are they made out of? Steel, copper, okay, all metals. Why? They transfer heat extremely rapidly through them. If we'd use some kind of insulating material, okay, like we could use the UV gloves, okay, if we built a pot out of an UV glove, why not? Okay? That's not going to work very well to cook our food because all that energy that we put in goes where? Displaced into the material itself. It doesn't pass through the material and get into our ultimate goal, which is the food. So we're using specific heat as a chain or something that's different between each material, and depending on what we want, okay, for that particular use, we may change our material. So when it comes to pots and pans, we want the amount of energy, okay, that goes in, okay, to immediately get transferred out the other end. Okay, so if I light a match, what happens to the temperature of the pan? Does it go up quickly or slowly?
From one match
Okay, I turn on the pot. Okay, I turn on the stove.
quickly.
Okay, it's going to heat up relatively quickly. But if I stuck the oven glove on top of it, does the oven glove heat up quickly? No one used an oven glove? How about those little silicon pads? Anybody use those? Okay, yeah, it's getting a little bit better. So the heat doesn't pass through. What we're looking at is the change in temperature. For the steel or our metals, what happens? We add in a small amount of energy and the temperature skyrockets. So if we look at our equation for a metal, let's say we put in 100 joules of energy. I know that doesn't look like 100, but there's 100 joules of energy. And we'll do equal masses. Let's just say 1 gram. How much does our temperature change? A lot or a little? A lot. So the temperature skyrockets within the pan. So we get a massive temperature change. Say 100 degrees Celsius. What number do we get? 1. Okay, let's take a look now at a new example. Let's look at our silicon heating pads. Actually, they're silicone heating pads. We add in that same energy, 100 joules. Okay, still the same mass, 1 gram. How much does the temperature change? Not a lot. All right, we throw it on there, we could probably touch it pretty much right away. So we'll look at within the same short amount of time span. So the temperature goes up 5 degrees. What's the number? I did pick one that we could do, right? 20. So the specific heat of our metal was 1. The specific heat of our silicone heating pad was 20. What can we say about our metals? They have very low specific heats. They will transfer the energy immediately through them. Okay? And we see that temperature jump right away. So this is a characteristic of all metals. This is also phrased as metals conduct heat, okay? And officially electricity. Our specific heat is just now a way to quantify how well they conduct heat. Okay, so if we've got a metal and we take a guess at their specific heat, we would guess that specific heat value to be extremely low. Because for an amount of energy we put in, the temperature skyrockets. Okay, and it's all based off of that relationship. Kind of vaguely makes sense. Okay, so how could I ask this on an exam, particularly where I can avoid dealing with numbers? Because we all know I don't like dealing with numbers. If we threw this in here, yeah, we could do a conversion, how much energy it takes to do something like this. Okay, but that involves a lot of mathematics, and we've already dealt with enough mathematics. Let's take a look at a fun exam question. Which of the following substances is expected to have the largest specific heat? This is a pretty challenging question. Kind of, sort of. Is it just as simple as looking at the periodic table? Not quite, because the periodic table gives you what? It gives you a bunch of information we've talked about. What information does it give you? We haven't officially talked about mass, but it does give you mass. Atomic number, again, we haven't talked about that. Metal versus non-metal. So when we look at our periodic table, everything to the left is a metal, everything to the right is a non-metal. Okay, that's a pretty important thing. What else does it tell you? What element is this? Everyone's got that one memorized, right? What element is that? Okay, let's try again. What element is this one? Really? Okay. This one. Oh, trying to go for 3. Yeah, you're right. It's hafnium. What does our periodic table give us? It just gives us the symbol. What is the answers, or what do the answers provide? Both the symbol and the name. So to answer this question, it's not just as simple as largest specific heat. It's using that periodic table, realizing the periodic table only gives us some information. We have to bring in more information. What information do we need to bring in? Periodic table helps us with metals and nonmetals. Okay, so where's calcium? Metal or nonmetal?
White metal.
It's on the far left of our periodic table. That is left, isn't it? Yeah. Metal. Cr. Metal. So that one's kind of nice. Shouldn't have said calcium. Should have just said Ca. Ca and Cr are metals. Do we even need to know what those elements are? Absolutely not. Doesn't matter. They're metals on here. So we can simplify some information. Ooh, next one says copper. It's been a rough day, apparently. What is our symbol for copper? Cu. So to answer this question, we need to know what the symbols mean, okay? What the names are for each of the compounds. So this question, in my opinion, is awesome because it tests on 3 or 4 different things. You have to bring all 3 or 4 of those different things together. Okay? Now that we know it's Cu, what is it? Metal or nonmetal? Next one. Pb, yeah, it's officially lead, so nice, but that doesn't contribute to our overall answer. We got lead, and it is a metal. What's the symbol for carbon? C. And? So, based on going through and doing that, can you answer this question without knowing anything about specific heat?
Yes.
Yeah, you actually can sneak out of this one. Why?
Carbon's only.
Which one of these things does not belong? The only one is carbon. If your answer was one of the other ones, we've got a decent amount of work stretched out in front of us. Okay? So we could jump to carbon. But let's go back to understanding what's going on with our specific heat. Largest specific heat means what? It's a conductor or non-conductor? Non-conductor. Our metals are all conductors, which means all of our metals we would expect to have low specific heats. Okay? So carbon, being a non-metal in comparison to the metals, will have the highest specific heat. We now have the answer worked all the way through. What if I'd also dropped a metal in there? It'd be really kind of obnoxious. Let's say it's gold, just for giggles. Au, by the way, is gold. Be careful with that. What's silver? Ag. Okay, make sure you keep those swapped appropriately. How do you answer this question? Said, just kind of for giggles.
I would say gold.
You don't. To be able to answer this question, you'd have to go through and know something about the specific heats. Metals tend to have low specific heats, but there is not a very nice, clear pattern across the periodic table. Okay? So you would not be able to answer this question at this point. If we give you all metals, you're kind of stuck.
Can I say that it would probably be closer to
As
the non-metals?
we would expect it to be closest or furthest, closest, sorry, to our nonmetals, because we kind of expect a general trend of it to become increasingly more non-metallic as we go left to right on the periodic table. Okay? We haven't gotten into periodic trends yet, and that trend does not hold true. Okay? Some trends do, specific heat does not. Okay? Questions about specific heat? You like that exam question? You should say you like that. It's kind of an important question. Conversions. So I've had a couple people, what was the exam question? What was the number? Do you remember it? Practice exam question number B, or letter B. So if you pull up the practice exam and you look at question B, had a lot of questions about that one. Right? People going, well, I have no idea what an angstrom is. Do you really need to have heard of or used a particular unit before to solve a unit conversion problem? Okay? No, it's completely irrelevant. What is relevant is what the conversion is. Okay, what do I mean by that? If I give you this question, how many meeks are in 3.4 stops? Have you heard of either of those units? Good, because I just made them up. Okay? To be able to solve this question, you need to know how to do that conversion. You need to know, is there a relationship between them? Okay, so if you come across this question and you see this, the very first thing that you should do would be do what? Pass it. I'll accept skipping it. Ask for the conversion. I would argue even before you raise your hand to ask for the conversion, check page 1 where I gave you a bunch of conversions. Sure enough, guess what? Page 1, I gave you a conversion. Okay, look at that. We now have the conversion. This is one I probably wouldn't put on the front page. I'd probably put it in the question exactly as it is here. All right? So now that we've got this conversion, I'm going to let you guys go through and do it. Okay? And someone's going to have to tell me the numbers because I didn't actually solve it. I literally made it up 5 minutes before class. All right? If you guys start, I want to know what the answer is. Okay? Because if you got the answer, you might as well just stop the question, right? What units do we want for our answer? What are we given to start with? Could deal with the conversion. I'm going to go with the standard format, our 3.4 stops. I'm going to do the abbreviation. Called it STP. Are stops equal to meeks? No. That means I have to do a conversion. So I'm going to have to do something in between here. Okay. Do stops show up in my answer? No. So they need to cancel. I have to get rid of that unit. So how can I cancel that unit? Where should the stops unit show up in my conversion factor? In the denominator. Okay. This is a trick question. What number do I put in front of it? Don't do it yet. Okay? Until we actually get what conversion factor we're using, what we're trying to relate, putting a number in is an awful idea. Okay? You could still be right. Don't get me wrong. Could still be right. But there is a high likelihood that it'll end up going wrong for you. Okay? So what unit do we want to get to? Where does that unit show up in our answer? In our numerator, which is on top, so I can include my meeks unit on top. Do I have a conversion factor that relates meeks to stops? Okay, that conversion factor is given in that equals format. Okay, 1 meek equals 4.5 times 10 to the third stops. Where does the 1 show up? In the conversion factor, up here. In front of meeks. Where should it show up in my equation? In front of meeks. I like that answer. 4.5 times 10 to the third shows up in front of, which means when we go to the answer, it should show up in front of the stops. If we look at our units, what happens? Stops cancel, and we have meeks. We can now punch it into the calculator and get our answer, which I'm going to guess it's going to be ballpark 7.5 times 10 to the minus 4?
Yeah.
Pretty good ballpark, not bad. So, how would we enter this into the calculator? Though everybody get this answer. Let's try that. Everybody get the proper 10 to the minus 4. Okay? No. Okay, where's the no? Okay, what did you end up with?
I just did it out. Mathematically did it out. I didn't get.
What do you mean?
Can you explain how you got to 10 to the negative 4? Can you explain spending.
Okay, so let's work through how I estimated it. So estimation is a really good skill for you guys to actually pick up. So let's take a look at this. I did a lot of rounding with this. Okay. So first off, what I can go through and do is pretty much ignore my units, because my units now are going to be meeks. Okay, so now I'm going to focus on the rest of this. I have 3.4 over 4.5. And I did a horrible job rounding this, but apparently I lucked out. 3 divided by 4 is roughly 75%, or 0.75. Okay. Times 1 over 10 to the third. Okay. I got that exponent value in my denominator. I don't like that. So what I'm going to do is swap that around. I'm going to say that I want to run this calculation in the numerator. To do that, what do I have to do? I have to change the sign in front of the 3. To get the scientific notation, I have to shift my decimal place 1 more over. There's my 10 to the minus 4. Okay. Did it really come out to 7.5?
Comes out to 7.5555, rounded.
That's awesome. Okay. So officially, with all those 5s, what's your official answer need to be? 7.6 times 10 to the minus 4. What do we say, meeks? Okay. Do you need to be able to do the estimation? No. You've got the calculator. You can go through and use the calculator. Where the estimation will come in handy is if you're checking your work. Okay, so if we looked at those numbers and said ballpark 7 something times 10 to the minus 4, and you punch it into your calculator and you get 7.5 times 10 to the 4th. 10 to the 4th versus 10 to the minus 4, drastically different numbers. Your estimation gives you a red flag that your answer is wrong. You need to go through and do the problem again. Okay? So estimation can be helpful. It's not a requirement. Yes?
When I do the calculator, just like it shows up there, every time you do 755,
755. What do you mean? Yeah, that's what we said, right? It's 5556. So we just carried out however many sig figs we wanted.
That's not the same as 10 to the negative 4.
The
answer in the calculator is going to be 755.555.
That's the other conversion. So you did the wrong swip with your 10 to the 3. So when you enter that into the calculator,
4
divided by 4.5, then what'd you do? Order of operations, when you punch that into the calculator, you did 3.4 divided by 4.5, quantity times. Okay? So you didn't actually put the proper 10 to the 3 in the right spot. This is why I like separating those out, because I can see that a little bit cleaner. It just comes from skill and practice on deciding what works for you. With your calculator, talk to me after class. We'll make sure we get the order of operations right so you can get to that answer. All right, other questions? No. No, I literally just made those up.
Is your extra credit problem going to be silly like this?
I won't answer that. Okay, at this point, I'm pretty sure, yeah. I'm at the point where we're at the end of the lecture as far as new material. So if you are happy, you understand everything perfectly, you don't need any help, you are more than welcome to leave, but please leave quietly. If you would like to see some more conversion problems, potentially exam questions, I do have, or not this exam, but I have the old exam up on my computer. I can pull that up and we can scroll through the specific problems and I can do those specific problems. But you need to kind of give me some ballpark idea on where I'm going. So, general consensus? More conversions. Those of you that are happy with it, you can take off. Just please leave as quietly as you can. What do we want for an answer? Okay, for those of you that don't know how to say that, you could just call it A, that's fine. So I'm going to go in my lower right-hand corner, angstroms, and you'll notice that I never leave space for the number. Okay, and that's because I'm going to get the number out of the calculator. I don't really care about that. What I care about is the work to get to that answer. So we want to make sure that the work for this, because it is a show your work question, is as accurate as possible. So I want angstrom as my final answer. What am I given to start with? 2.27 times 10 to the minus 13 kilometers. I heard a couple things get tossed out there. I heard that number, and I heard someone also mention radius. Okay, and this has been mentioned a couple times. You might panic a little bit here and think, oh crap, I just moved into a geometry class. I've got to worry about what the formula is to calculate the radius. Before you panic, I give you the radius and I ask for the radius. We don't need to know any geometry. We're just converting a standard distance. That distance just happens to be a radius. Okay? So we're starting with the kilometers. So as we would do with all of our conversions, I want to get rid of the kilometers, so I will put those in the denominator. I want angstroms. Those of you writing may get frustrated by this. Sorry, deal with it. Do I have a conversion factor between kilometers and angstroms? No. Okay? So now I can go back, check the front page, check the information given in the question. Am I given a conversion factor there? Ish. What's the conversion factor I'm given? Angstrom to meters. So I do have a way to relate angstroms to something. It's just not kilometers. Okay? So I can't convert angstroms to kilometers. Can I convert kilometers to something else?
Yes.
Meters. Which could work out pretty nicely because I have a conversion between meters and angstroms. Okay? Now, again, kind of addressing the overall process behind this, we would go, is that conversion factor given to me? We check the question. Is it given? No. Is it on the front page? No. Guess what that means? I expected you to memorize it, and I've said it multiple times. Kilo, milli, and centi. You need to know those. The K is for kilo. You need to know that conversion. What does the K mean? 1,000. Okay. Also known as 10 to the minus 3. I want to kind of keep that, 10 to the third. That needs to go up top because it's trying to equate the kilo below. What number shows up in front of kilo? 1. If we track the units, kilometers cancel and I now have meters. Does meters show up in my answer? No. So I need to do yet another conversion factor where I cancel out the meters. So meters must show up in the denominator. What conversion do I want in the numerator? Angstroms. Do I have a conversion between angstroms and meters?
Yes.
Yeah, it's given to me. What number shows up in front of angstroms? What number shows up in front of meters? Okay. What happens with my units? Meters cancel. What units do I have now? Angstroms. This is where if I was writing out my work, I would drop another equals here. I would go through and do the math with the numbers and end up with angstroms. From my own personal perspective, I like to simplify. I didn't do any mathematics with the actual numbers in front. The only thing I've really changed is the tens to the powers. I didn't do any addition or multiplication, division, by anything else. So I go through and I would say this is 2.27 times 10 to the negative 13, right? Times 10 to the third. I won't change those numbers because they're already in a nice happy place. They're in my numerator. I'm okay with that. The next one, the 10 to the minus 10, is in the denominator. If I want to bring that into the numerator, what do? I make it a positive. This is now equal to 2.27, and because my base is the same in each of those cases, I can now just add the exponents. 10 to the negative 13 plus 3 plus 10. 13 plus 3 plus 10 is 0. 10 to the 0th power? 1. 2.27 times 1? 2.27. My answer, without even touching a calculator, 2.27 angstroms. Okay. The approximations and the steps I went through can be a bit dicey for students to deal with. You're fine to go through and enter it into the calculator. Make sure you approach your orders of operation correctly, and I will talk to you about that after class. Okay. So if at any point you're getting a different number than the 2.27, you're doing the order of operations wrong when you enter it into the calculator, talk to me, and we'll go through and make sure that you've got the calculator, or you could punch it into the calculator correct. This is a show your work question, meaning almost all of the points are for the work. So if you came out with 2.27 times 10 to something, but you had this work, you would get 2 points, even though your answer was wrong. All of your work is spotless. You get most of the points because it is a show your work question. Okay? If it is strictly multiple choice, sorry, you lose all the points. Okay? So focus on the work. What if it's just a straight multiple choice question? Should you show any work? Absolutely. Okay? That's another kind of pet peeve of mine. I get the multiple choice exams, I look through it, someone did horribly on the multiple choice, and it bothers me. So I go through and look at their multiple choice, say maybe they bubbled something in wrong, so I look for that, I don't see that. Then I go through and look at my key, maybe I bubbled the key in wrong. Then I go to their exam, and I'll look at all the multiple choice questions. And almost invariably, what do I see for each and every single question? Just the question, with absolutely no work. Every single question you can write something for. Okay? Show that work.
So if
Yes.
I just set it up, at least set it up, and then I'm not putting all that other stuff like, okay, you're putting times 10 times 10 times 10.
You're fine.
That, but at least I have
The-
like how I set it up.
The only work that I would look for to get points would be right here.
Yeah.
So I look for that format in any order, doesn't matter the order.
It's not gonna lie, I put it in,
Yeah, and that's fine. I go through and did that because I don't have a calculator handy. So that's the only reason.
So do you want the work in what part? Because we're gonna do just scatter,
So
do we need
this is a show your work question. You'll notice the space between those questions is pretty massive. I left you lots of space to provide your work. That's where I want to see
So
it.
it's okay to write on the,
It is okay to write on the exam. Exactly right. Everybody okay with this question? Okay, so let's scroll through to one that's not a show your work. If I can find my mouse. Please don't get dizzy. Term for an investigation that entails performing an experiment, proposing a hypothesis, testing a hypothesis, failure, repeat, and stating a theory or a law. Okay. Almost everybody jumps straight to an answer. I would argue that you could show some work here. It may not be a lot of work, but you can still do it. You've got performing an experiment, proposing a hypothesis, testing a hypothesis, failure, repeat, stating a theory. I'm looking at something that has 1, 2, 3, 4, 5 parts. My answer needs to have a lot of individual components behind it. Okay, this is a chemistry class, so why did you not say chemistry? Does chemistry just apply to this, or can we look at other things? We could look at other things. Okay? What this is looking at is a in particular way to approach a problem or a thought process. The best answer fits our method. Minimal work, but it's at least something. If you don't want to write it, that's fine. I don't care. Okay? There's no skin off my back or nose or whatever you want to call it. Okay? But it's getting some information down so you can kind of think about how you were approaching that problem when you go back and check your work. Which brings up a good point. First exam, nearly everybody last semester finished within 30 to 40 minutes. Turned in the exam, I left early. The average was something like a 65%. Okay? Everybody left early, which means you turned that exam in knowing that you knew all of the answers. Because you turned it in early. That's what it means to me. Okay? If I have to chase people out of the room, I'm happy about that, because that means you're fighting to put down the answers and get the information down. Take the full time. Check your work if you've got it. Okay? When you turn it in early, it's either that you know absolutely nothing, in which case the average should be a 0%, or that you know everything. Those are your only two options. Okay? Should we try another problem real quickly in the 2 or 3 minutes we got?
Can you go
Yeah.
back real quick? I'm a little confused on this, on the last question. I know it's a bit past it, but your conversion was 2.7 times 10 to the negative 13.
Yep.
Times 10 to the third times 10 to the 10th. So when it
Yep.
came down to it, it canceled out, right? But where did that positive 10 come from?
So the positive 10 came from, so our calculation initially had, let's see if I remember this right. It was 1 angstrom over 1 times 10 to the negative 10th meters. This is the same as 1 angstrom divided by 10 to the negative 10th meters. Okay. If I want to bring this calculation to the numerator, I just change that sign.
So I was confused. I was like, well, if it was, you know.
It's a trick that some people are aware of and some people are not. For people like me that are calculator intolerant, it's one that I've picked up because it allows me to check work pretty quickly.
All right, good to know. Thank you.
Other questions?
Do you ever put in the 2.27 that given number?
We started. That was the very first number we started with.
Okay.
Yeah. Should we try one more? Diamond weighs 1.33 carats. What is the mass in grams? What answer do we want? We want grams. What do we start with? 1.33 carats, which I'm going to abbreviate CTS. Do carats equal grams? No. So what do we need to do? Conversion factor. Where should carats show up in my conversion factor? Denominator. What do I want to show up in my numerator? This is the ideal target. I want grams. Do I have a conversion factor between grams and carats? No. So we check the whole exam. It's not there. Raise your hand. Sorry, you got to do it without it.
You're supposed to memorize.
Okay. Do we have the conversion factor of carats to something else? What number shows up in front of milligrams? How do you know it's 200? This is a bit obnoxious on this. I would probably actually rewrite this out on the whiteboard just because the numbers split across lines. But that 200 is tied to the milligrams. What number shows up in front of carats? What units do I now have? Milligrams. Are milligrams equal to grams? No. So, another conversion factor. What unit do I want in the denominator? Why? So that it cancels the units. What unit do I want in my numerator? Because that's what I'm looking for. Do I know a conversion between grams and milligrams? What is that conversion? So this is where we got to be careful with our conversions. The way I've been teaching you to do this is that the milli is what you need to look up. What does milli mean? 10 to the negative 3, which means I need the 10 to the negative 3 in front of the grams. The power always adjusts the base unit. What number shows up in front of the milligrams? 1. Yes. What conversion factor did you want to use?
Why can't you say 1 gram over 1,000 milligrams?
Okay, James, I'm going to call you out. What's the relationship between those? Not because you're doing work there. What's the relationship between this conversion factor and this conversion factor? And maybe as a little bit of help.
It's the same thing, it's just one is
I just swapped where I did the calculation. They are identical. The only reason why I'm showing the bottom one is because the powers of 10 you should always apply to the base unit. Okay? It's easier to memorize. You're good. You're good. We need to get out of here. So at that point, we'd run our calculation into the calculator, and we've got our final answer.